Today we are going to go over question 14 on exam 2, part 1. Question 14. A steady state, steady flow adiabatic turbine receives 20 kilograms over seconds of steam at 200 degrees Celsius, 300 kilopascals. A second flow of steam enters the turbine at 150 degrees Celsius, 200 kilopascals. The exiting flow of 45 kilograms over seconds is at 100 kilopascals with a quality of 70%. A. What is the power output or input in kilowatt for the turbine? We will first draw our system with two flows entering a turbine and an exiting flow that can be labeled as 3. Some assumptions we have are: since the situation is a steady state, steady flow, SSF, the sum of the exiting mass flow rates are equal to the sum of the entering mass flow rates. The heat transfer is equal to 0 since it is adiabatic. The kinetic energy difference is equal to 0 because no information about the velocity or pipe diameter was given, and the potential energy difference is equal to 0 because no elevation information was provided. We will then write out all of the given information on each flow. Given that we need to find the power, we will use the first law of thermodynamics. From there, Q dot is equal to 0, and the kinetic energy and potential energy portions can be canceled out. This leaves only H to be determined. We will now find the enthalpy for flow 1 and 2. We have our given information about each flow. From there, we can use table C3 to determine H1 and H2. H1 being 2,865.6 kilojoules over kilogram, and H2 equal 2,768.8 kilojoules over kilogram. Next, we will determine H3. From the given information, we can determine the phase of the flow to be a mixture of saturated liquid and saturated vapor, since the value of quality is between 0 and 1. Using table C2 and equation H3 is equal to HF plus X times HG minus HF. Along with the values from HF and HG, we can determine H3. Plugging in our values, we find that the enthalpy is equal to 1,998.07 kilojoules over kilogram. Also remember to double check that your found value is between HF and HG, which in this case it is. Taking a look at all of our given information and determined values, all there is left to determine is m dot for flow 2. From our previous assumption, m dot 1 plus m dot 2 is equal to m dot 3, we can rearrange the equation to solve for m dot, which is 25 kilograms over seconds. From our previous equation, we are left with W dot is equal to H2 times m dot 2 plus H1 times m dot 1 minus H3 times m dot 3. Plugging in our values, we can find work to equal to 36,619 kilowatts. And since the work is greater than 0, the turbine produces a power output.